are these? What actually are these? What actually are these radio galaxies? What are they made of? When you ask that question, you can break it down into a number of different questions, such as what is the lobe actually made of? What are these structures that we're seeing? What particles are in there? What magnetic fields are in there? We know, because we're observing synchrotron radiation, that there are at least charged particles and magnetic fields in the lobe, but there could be other things in there as well. If we look at the jets, we can ask questions about the jet power. And if we look outside the lobes, we can ask questions about what environment are the lobes propagating into, what is the density, pressure, and temperature, and therefore what's the environmental impact of those radio galaxies. There are a number of other questions we can ask as well. I put some others in brackets. I'm not going to talk about the ones in brackets here, but I'm happy to talk about them in the questions, such as how do these jets fundamentally get generated by the supermassive black hole. Okay, so the environmental effects of radio galaxies are actually pretty obvious, and they're quite well observed. So let me run through the story that I'm going to be relying on for the next part of the talk. Where you see the radio lobes, as in this example, this is another radio galaxy, Cygnus A, the famous one, and what we're seeing here is observations of the radio in red, the X-ray emission from hot gas around it in blue, and the yellowish colors are optical observations. Okay, so when you see these radio lobes, you can straight away say, well, we know there are electrons, relativistic electrons and magnetic field in the lobes, and that gives you an estimate of the pressure in the lobes. You can in fact say there is a minimum pressure. It can't be less than such and such a value. And those values are quite high for interstellar space. And so that pressure must be balanced by something external to the lobe. Because if that were not the case, the lobe would expand very, very fast at the speed of sound in that lobe, which is relativistic, and it would disappear. So that implies that when you see a radio lobe, there must be a high density environment around it. Now, there's a number of lines of evidence, and we'll look at these in more detail in a minute, that the lobes are not just passing through that environment, they're actually making holes in the environment. They're inflating cavities. We've known that for many years because polarization in the radio implies that there is not the same density of thermal material inside the lobes as outside. So, but if you take a fluid and you blow a bubble in it or inflate a cavity, you're doing work, and that means that work's being done on the external environment. And so before we ever observed this process, we knew it must be happening. The radio galaxies, just by existing, have done work on their environment. You can see some more discussion of this and a lot of other background material in a review article that Judith Croston and I wrote last year, which you can find on archive. So, okay, so to illustrate the how we think this works now, here's a numerical model. This is a visualization of a numerical model which incorporates a lot of the relevant physics that was done by me and Martin Krause a few years ago. Let's see if I can just play that again because it's quite quick. So you can see in this, what you're seeing here is the orange colors are synchrotron radiation from the simulated radio lobes. The blue colors are the environment, and you can see a shock being driven into the environment. The lobes are expanding supersonically, so they drive strong to moderate strength shocks, which you can see in the end frame here. So this is the bow shock driven by the radio lobe. Close to the midpoint, we actually have rough pressure balance between the lobe material now in red and the external material now in blue. So those simulations confirm what we would have predicted from early modeling, which is that there is this environmental impact for the radio galaxy. Okay, so why does anybody care about this? We people who worked on radio galaxies, I did my PhD in the 1990s, and at that time nobody had any idea that radio galaxies were useful for anything. Really, it was just a curious thing. The universe does this. Some galaxies produce these radio loud AGN. So what? Well, it turns out there are two important reasons why we need radio AGN. And they're basically the same reason in two different guises, actually. you're probably all aware that cosmological models require some sort of AGN feedback to regulate the growth of massive galaxies. So to prevent the most massive galaxies growing to very large masses, this is shown and has been known for some time, shown in these plots. So these are taken from an old paper by Darren Croton, showing what you would get if you didn't have a feedback process for a galaxy mass function, and what you actually do get. And you need to incorporate AGN feedback to stop the most massive galaxies growing very much larger and brighter than they actually are. So that's one thing that AGN are needed for. And another thing is when you observe clusters of galaxies, you see that they emit X-ray radiation, as shown in this image, which is just an image of an ordinary cluster of galaxies, no radio here. So you can see many galaxies, and then you can see the purple halo, which is the X-ray emitting gas. That gas is radiating X-rays, which means it's losing energy, it's cooling, and it ought to collapse inwards and accrete onto the central massive galaxy. And in fact, it doesn't. And this was known as the cooling flow problem for some time. I mean, people believed that this really did happen, and then they discovered that it didn't. And again, if you can produce something that offsets that cooling by putting in some extra energy, then you can stop that cooling flow from happening. And those are the same problem written in two different ways, because what you're talking about, stopping the X-ray gas from cooling, is the same thing as saying you're stopping cold gas from falling onto the central galaxy and causing it to grow and form more stars. And radio galaxies clearly are having an effect on the hot gas around the central galaxy in the local universe. So the question that I've been asking is, well, how can you quantitatively say, do they provide enough energy to actually do the job that they're required to do in cosmological models, and compare that with model expectations over cosmic time? Okay, so in order to set about doing that, we need to get some background. So one of the things that I have to tell you, this is kind of, radio galaxy history, but it's important history, is about the two types of radio galaxy. There are actually many more than two types, but an important distinction is between what are now called Fanneroff-Riley class 1 and class 2 sources. I'm sure many of you know Bernie Fanneroff. Julia Riley was my thesis advisor. So this goes back a long way. Fanneroff-Riley class 1 objects are these things that have bright centers and then fade out towards the edges. So we see a core, we see a bright jet, and we see a gentle fading in these high resolution images of a classical FR1 type object. Fanneroff-Riley class 2 or FR2 objects are brightest at the edges. They have faint jets, if the jets are there at all, compact hotspots at the end, and these kind of diffuse lobes. Now, what Fanneroff and Riley said was that low radio power sources are FR1s and high radio power sources are FR2s. And that's not really true, but there is a strong tendency for the most powerful sources to be FR2s. You can read some of more details about this in a paper by Beatrice Mingo, my former student, from 2019. Again, you can find on the archive. So, however, I'm just going to ignore the subtleties here and talk about FR1s and FR2s as they mean kind of low power and high power radio sources from now, because there's a physical distinction which we'll get onto between these things. So let's now think about what's inside the lobes. So if you look at X-ray observations of radio galaxy environments, I've already mentioned that the radio galaxies inflate cavities. So what do I mean by that? Well, you can see them in these X-ray only images. This is showing the hot gas, and there are holes in the hot gas. Right? So for example, in this image of Cygnus A, you can see a hole here and a hole here, and you can also see a hole here and some other holes here. And if you think about it, this means that this doesn't make sense. You can't have holes in hot gas unless there is something that's stopping that hot gas from just expanding into the holes. So that's the evidence that the radio lobes are not full of hot plasma at the same temperature as the surrounding material. Similarly, in this beautiful image of Perseus A, you can see many cavities that have been inflated by different episodes of the radio galaxy as it turns on and off. Now, when you look at those cavities, you can do a calculation. You can say, well, if those cavities are supported by material from the radio lobes, then is there enough material in the radio lobes to actually prevent those cavities from collapsing? And in the case of the Phanerophoridae class 1 objects, we think the answer is no. The electrons and fields on their own can't supply enough pressure to balance the external thermal pressure. This is something that Judith Croston did a lot of work on, starting with her PhD work and carrying on for a number of years. And essentially, we can see a difference between the Phanerophoridae class 1s and the Phanerophoridae class 2s in terms of the ratio between the internal pressure inside the lobe and the external pressure outside the lobe. And that should always be 1 or greater. But for Phanerophoridae class 1 objects, it appears to be less. The lobes appear under pressured. So we don't really know what's going on there, but we think Phanerophoridae class 1 objects have an additional contribution to the internal lobe pressure, which we can't see. So particles which we can't classify in some way. So they're probably very hot thermal material. But these things don't radiate. So it's quite complicated to understand FR1 radio galaxies. Fortunately, it turns out that FR2 radio galaxies are quite easy, and they do behave as we might expect. And essentially, it looks as though the lobes are just filled with the radiating particles of the magnetic field that we know about. So that's really useful. You can then ask, what about the lobe magnetic field strengths? How do we measure those? And again, there's a complicated story that I won't go into, but you can measure those using X-ray telescopes as well by detecting a process called inverse Compton radiation, where the electrons in the lobes scatter mostly cosmic microwave background radiation photons into the X-ray. You can see that, an example of that in this radio and X-ray image of pictorial ray, where the X-rays here are showing inverse Compton emission from the lobes. Using that, that gives us a measure of the number of electrons in the lobe, and from that and the synchrotron radiation, we can infer magnetic field strengths, and we find that typically the magnetic field strengths are energetically not dominant, but subdominant with respect to the particles. So we can get that particular diagnostic out for those Phanerophoridae class 2 objects again. It turned out not to work nearly so well for the FR1s, and so that's another reason why we don't understand those objects so well. Okay, so next we can think about how the radio galaxies evolve. So a common way of describing the power, the evolution of a radio source is this power linear size diagram, which you can see on the right. So what this is showing on the x-axis, you can see the size of an object. This is log size in parsecs in this presentation. So this is 1 kiloparsec, this is 1 megaparsec. And up here you can see the radioluminosity expressed in watts per hertz at 1.4 gigahertz. So this goes over 10 orders of magnitude in radioluminosity. And at any given time, a given radio source is somewhere on this plot. It has a measurable linear size, it has a measurable brightness. But sources are going to evolve on this plot with time. Generally, they're going to evolve to the right because they're going to get bigger with time. The jets carry on going, so they're pushing against the external medium, so the sources will grow. So you can define evolutionary tracks on these diagrams. And those tracks depend on jet power, radio source age, environment, and other effects. Different types of radio source, I'm not going to go into the details here, but various different families of radio sources can be plotted on this diagram, which I owe to Miranda Jarvis, who made a particularly nice version of it, which we stole for our review paper. We can therefore try to understand the source's evolution by looking at where they are on these diagrams. And the sort of modeling we can carry out looks like this. So using using numerical simulations like the one I just showed you, we can understand the evolution of radio lobes and the gas that surrounds them, and therefore understand how energy is transported from the jets to the lobes. But what you can then do is try to make a semi-analytic model that gets the same results without having to do a numerical simulation every time. And that's been done by several people, including me, but also Stas Shabala and his group. And you can see the sorts of results we get here. So these are tracks in the power linear size diagram for sources of different jet powers, many different jet powers shown here, and then many different environments. And you can see the general shape of the track in these diagrams is to go to start high, to go down, and then to go up again, and then down again. And so by the time for sort of observable sources on size scales of kiloparsecs, we're expecting a sort of smooth curve for a given radio source in the power linear size diagram. Okay, so we can if I know all the important parameters of a radio galaxy, such as its jet power, the environment it lives in, and how old it is, I can tell you how big it is likely to be and how bright it's likely to be, which is all very well. And you can use that in one of two ways. So if we want to understand the impact of a radio galaxy, you can do kind of detailed observational modeling. And an example of this is from this paper by Vijay Mahatma in 2020. Vijay was my PhD student and has now moved on to a postdoc in Germany, but he did this very nice work, detailed studies of a couple of Van Ridey class 2 objects. So he took multi-frequency radio observations, he took deep X-ray data, so these are the same two objects superposed on X-ray images, and then you can model the shocked shell, the region of gas that's been shocked by the radio galaxy. So here's some of the modeling and spectral fits that he did in the X-ray. And then you can fit the dynamical models, which we've got, so the analytical models that I showed you earlier, to all of that data and try to get out how old is the radio source, what is its jet power, how much work has it done on the external medium, and so on. And we can do that, and for individual sources, we can calculate all of those properties, but that doesn't tell us anything about the population, and it never will, because X-ray observations are extremely expensive, and even with survey instruments like eROSITA, you just don't have the data you need for most sources. There's a lot of radio sources in the sky. So although it's really nice to be able to do this, we can't do it for everything. How do we get around that? Well, of course, there's a way around it. And the way around it is to realize that the simulations actually tell you something else. They tell you that almost independent of environment or jet composition or any of these things, the amount of energy that's put into the external medium is about the same as the amount that stays in the lobes, roughly speaking. So if I show you a radio galaxy and I say, how much work has it done in on its external environment, then even though you don't know what the external environment is, you can say, if I calculate the amount of energy that's in the lobes, it's about the same as what I can see, as what's been done, what's gone into the external medium. So in other words, lobes can be used as calorimeters, at least for these powerful radio galaxies, because we don't really understand the lobe contents for the low power objects, as I said. That is really important because it means without doing a really detailed survey of the environment, we can start inferring the effects of the population's feedback just by looking at radio data. So where do we get our radio data from? This brings me to the second part of the talk, which is basically an advertisement for LOFAR. So to get the radio data, we use LOFAR surveys. VLA surveys are just not good enough because they don't have the UV plane coverage for the radio astronomers in the room. That means they're either not sensitive to large scales or small scales. Next generation instruments like LOFAR and like Meerkat and like the SKA will be have really good UV plane coverage, and you can make observations that show you all of the radio source at once. So we're using LOFAR because it exists and it's a really good survey instrument. And we're using the LOTS survey, which has this really impressive northern sky coverage. We have about 6,000 square degrees worth of northern sky coverage right now, as you can see from this plot of the sky coverage, with green being data that we have in hand. So the LOTS survey in detail, it's a survey of the northern sky at 144 megahertz. It's wide area survey. We get many tens of square degrees per pointing, and we tile 8L pointings across all the sky. We've also got deep observations of many famous fields, and I'm not really going to talk about those. We get 6 arcsecond resolution at the moment using the Dutch Xray, and that's 6 arcsecond resolution is good enough to get the optical ID of the radio galaxy, so to be able to say what galaxy does it belong to. It's really important to have that high resolution. Other surveys that have been done of wide areas that do include extended structures like NBSS just don't have the resolution to actually tell you what the galaxy is that they belong to. There's a public part of this survey which is about 400 square degrees and is available already. You can go to the website and download it. There's a wide area release, data release 2, which is this 6,000 square degrees. We're hoping to release that this year or the next calendar year. Okay, so with large samples like this, we can get large samples from lots, and that means we can see all phases of a radio source's lifetime. So here's this, the sky isn't actually this full of radio galaxies, this is just a montage, but you can see the sorts of structures that we can see in lots. So optical and images in the background, and then contours showing the radio, many double radio sources. And in the data release 1 data, which is the basis of what I'm going to tell you now, we had about 300,000 sources in the value-added catalogue. So that's objects where we tried to do an optical ID, and we were able to get a flux complete subsample of 72,000 objects with good spectroscopic or photometric redshifts. So that's a lot of radio sources. Famous radio surveys like the 3C survey get you a few hundred radio sources, so we're greatly increasing the sample sizes. Now, of course, not all those radio sources are active galaxies. Star-forming galaxies produce radio emission just by being star-forming galaxies. So AGN selection is really important, and the details of this are quite complicated. The gold standard for AGN selection, I think, is to actually know the star formation rate of your host galaxy, because star-forming galaxies have a quite tight relationship between their star formation rate and their radio emission, which you can see in this plot here. So this is taken from Gulai Gherkin's work. Star formation rate on the bottom, radio luminosity on the y-axis, and you can see these star-forming objects, the red things, classified as star-forming galaxies in SDSS, lie on this very tight read locus. And then there's a whole bunch of galaxies that lie above it, where they have more radio emission than they should have given their star formation rate, and those things are our radio AGN, and that's what we want to select. So if we knew the star formation rate for every galaxy we looked at, that would be great, but we don't. And so you have to do a bunch of other things to try to separate radio AGN and star forming galaxies. And you can read about this in Pepe Sabater's paper, for example, where you have SDSS data, but you don't have a good star formation rate. You can make use of spectroscopic classifications. Where you don't have either of those things, you just have to work based on colors. And we quite crudely ended up in my paper on this, just cutting out objects that look like they have star forming colors by making a wise color diagram and cutting out a region where the star forming galaxies tend to lie. So you won't get perfect results by doing that, but you will be able to select out a bunch of AGN. And you can see that that the things that remain lie in locus, one locus that is basically elliptical galaxy colors, and another that's basically quasar type objects, either unobscured or obscured quasars. So when we did this, we got a number of interesting results, which I just want to go through very briefly. One key result is that the most massive galaxies, so when you go to the very high end of the galaxy mass function, you almost always find a radio AGN, so an object that has a significant radio excess over the star formation. You can see that on this plot here. Maybe the left one is the easiest to see it on. So stellar mass on the bottom, we've got fraction of radio AGN on the y-axis, and we're putting different radioluminosity cuts. So you can see that as you go to, if you take the lowest radioluminosity cut, then once you get above 10 to the 11 solar masses, every single galaxy has a radio AGN brighter than that. And as you go up in radioluminosity cuts, you find that those numbers go down, but every galaxy above, say, 10 to the 11.5 solar masses has a radio AGN above around 10 to the 22 watts per hertz at 150 megahertz. So that's telling you that whatever the process is that generates radio AGN, it's pretty universal, at least in the local universe where we can do these calculations. Now, my interest is in going to higher redshifts. So we generated a much larger sample than was used by Sebater et. We went out to about redshift 0.8 because that's where the galaxies start running out. This was based on Pan-STARRS observations, and Pan-STARRS depth kind of stops working at redshift 0.8. And we had about 23,000 objects that we classified as radio loud AGN. We excluded radio quiet quasars, which sit over here on this K-band versus radioluminosity diagram. So this is the radio quiet quasar branch, and we're not quite sure whether that radio emission is due to star formation or not. So we just excluded those, and we excluded the star forming objects, obviously. So we're left with what we think are genuine radio loud AGN. You can plot those objects on one of those power linear size diagrams. So here's yet another version of this diagram. So again, size on the bottom. So this is in kiloparsecs, 1 kiloparsec to 1 megaparsec, and radioluminosity up here. Okay. This is all 23,000 sources plotted on a density plot. On top of them, these pink dots are the 3C objects for comparison. So famous bright sample of northern radio galaxies. And then overplotted, you can see tracks of different jet powers from 10 to the 35 up to 10 to the 40 watts from my analytical modeling. So you can see the sorts of curves that we expect objects to describe. Okay, so we've got a reasonably complete sample, but there's one incompleteness here, which is that there's a surface brightness limit. So in this bottom right-hand corner, you can't see sources simply because they once they get big enough to be over here on the x-axis, they're too faint to be detected by LOFAR. So it turns out that we kind of get reasonably complete. This is, we're not really affected. We run out of sources before we run out of surface brightness sensitivity, only up at these powers of sort of 10 to the 26 watts per hertz. So we're reasonably complete for the most powerful sources, but we run into serious incompleteness for low power objects. Okay, so what we can do with this is try to work out for the places where we are reasonably complete, what does this imply for the distribution of lifetimes? Because the distribution of lifetimes controls the distribution of sizes. So this was the first thing we tried to do. And we simply simulated a distribution of lifetimes through the analytical models and compared it to what was observed. And so interestingly, you can make a very simple uniform lifetime distribution. So basically sources live for an almost a fixed amount of time, and they have a reasonable probability of lying within that range, the kind of uniform probability. And when you do that calculation for powerful sources, you find that actually matches the distribution of sizes very well. So what you're seeing here is blue are the simulated population, green is the actual observed population. You can see that the blue and the green agree very well. The only difference is that the very smallest sources, we can't actually measure the sizes because they're unresolved, but you can see the upper limits, and the upper limits agree pretty well with the simulated data. And this completely breaks down when you look at the low luminosity objects, where you would predict a much broader distribution of sizes, even taking into account the surface brightness limitation than you actually get. So something funny is going on with the small sources, the low power sources, sorry. And again, this is yet another reason why we think we don't really understand low power radio sources. But it's encouraging that we can model the powerful sources so well. So if you then just say, let's try to use the source's position on the power linear size diagram to work out what its jet power is, then that's something you can do. So what we're doing, what we know a source's redshift, we know its radio power, we know its size, and we have priors on the environment it could be living in, the lifetime, because we just looked at that, and the jet power distribution. So this is an inference problem. And we feed in the observational selection criteria, and we try to infer the jet power based on all of those things. So the sort of inference diagram we can draw here for the this is a projection of the actual inference onto the power linear size diagram, just to give you an idea of how it works crudely. So you can see essentially what we're saying is that if a source is in this a given particular place on the power linear size diagram, then its jet power is about whatever it is. So, you know, for example, if we're here, to be up here with a radio power of 10 to the 29 watts per hertz at a megaparsec linear size, you need a jet power in excess of 10 to the 39 watts. And if you're down there, you need a much lower jet power. So it's a little more complicated than that, because because redshift matters as well, but we can operate this kind of inference and try to work out the jet powers for all our sample. And by doing that, we can construct this thing, which is a kinetic luminosity function. So this is really just saying how much, for a source of a given given jet power, how many sources are there with that jet power in the universe per cubic megaparsec. So low power sources are more common than high power sources. That's not a surprise. In fact, this looks pretty much like a power law. And interestingly, it doesn't evolve very much with redshift either. So this is all well and good, but we can do something straight away with this that's very interesting. So if you take that kinetic luminosity function, and here it's just multiplied by the jet power. So this is like a nu f nu plot. It's just telling you where is most jet power coming out. This tells us that the jet power in the dominant contribution to the total jet power of all the population is actually from the most powerful sources, which is really useful because those are the ones we understand. Then you can just integrate this kinetic luminosity function, and that tells you, that gives you a number in watts per cubic megaparsec, which is not a unit you often see, but it's telling you how much energy is being put into the external medium. Well, it's going up the jet in total, sorry. How much energy is going up the jet in total for all radio galaxies per cubic megaparsec in the local universe. Okay, and that's the answer, 7 times 10 to the 31 watts per cubic megaparsec. Now what can we compare that with? Well, the obvious thing to compare that with is how much energy is being lost from the environments of these objects by cooling. So we know that that most radio galaxies are living in X-ray emitting environments. We know what the X-ray luminosity function looks like of clusters and groups in the local universe, and you can integrate that. So here's the X-ray luminosity function. We just integrate that up, and we get a number which is the cooling rate in the local universe, 4 times 10 to the 31 watts per cubic megaparsec. Well, you know, we set out, remember, to ask the question, can the radio galaxies prevent the cooling energetically? Can the population of radio galaxies prevent cooling in the of the X-ray gas? Well, you know, these numbers are astonishingly close. I'm still amazed at the fact that they come out even in the same ballpark, because nobody knew that was going to happen. So yes, the answer is yes. The amount of energy going up the jets is about the same as the amount of energy that's being produced by the X-ray emitting material. It's way too close to be a coincidence. So so that answers one of those questions. The population really can do this job. Now, do we believe this? Well, there's a lot that we don't really understand. So we don't, at the moment, know the environment of each radio galaxy. And I told you earlier that environment is important in determining how bright the radio emission is. We know that our models work best for classical double FR2 type objects, but if you look in the LOFAR surveys, as you can see in these pictures on the right, there are plenty of objects that aren't classical doubles. We do include remnant objects, but we make a very simple assumption, which is that a jet is continuous and turns on, has the same power, and then turns off again. That's probably not true. We don't really understand FR1 radio galaxies, as I've said. And a really crucial thing, which is one of the things I want to focus on next, is where the energy actually goes when it goes up the jet, because it might not go to the right place. So although energetically the radio galaxies can offset the cooling, that doesn't work if the energy of the radio galaxies is all being deposited on scales where the cooling isn't happening. Right. So we need to look at that. And there's some evidence that things are very complicated with some of these low power sources in particular. You can see the radio lobes tail off into these very complicated structures where the electrons are actually mixing with the external medium. We haven't really taken account of that sort of feedback process at all in our models, but I think it's actually quite important and affects the intracluster medium. So, for example, you can see this here in the Coma Cluster. This is a LOFAR image of the Coma Cluster, showing the connection between radio galaxies, these small structures, and very large halos of radio emitting electrons that are completely mixed in with the hot gas in Coma. So we're still working on understanding how that actually works as a feedback process. But eventually, of course, the energy in those electrons is going to be thermalized and it's going to be dumped into the external medium. Okay, so what's going to happen next? Well, we've got this data release 2 coming, and I think we're going to be able to do a lot better with the AGN samples. We're starting to construct these now, and it's looking really good. We'll be able to increase the number of AGN by an order of magnitude. I'm just showing you a fly through a tiny piece of DR2 in this slide, just so that you can see just how beautiful the data are. In addition to being much wider area, they're also they're also greatly improved in processing from our first data release, and it really does show. We can get better photometric redshifts, and fairly soon we'll be able to get spectroscopic redshifts for all of these galaxies, which is also important, using the Weave LOFAR project. And my hope is we'll be able to do environmental inference for these AGN. I have a postdoc working on this at the moment. We're using citizen science to help us get the optical identifications. This slide's slightly out of date. I think we now have about 800,000 views of LOFAR sources, and we're a bit further through data release 2 through the optical ID process, and I'm just about to get started and trying to write a paper about this. Part of the reason for mentioning this, of course, is that if anybody really wants to see some LOFAR data, a great way of seeing some LOFAR data in action is at lofargalaxyzoo.nl, where our citizen science project is located. Uses the Xeniverse platform. I mentioned Weave, and this is coming. First light is probably going to be in a couple of months, I hope, and this will get optical spectroscopy for a large number of LOFAR sources, and there's all sorts of cool things we can do with that. I don't have time to talk about this, but I have a long-standing interest in the the accretion modes in radio galaxies, and one of the things that we LOFAR will do will really nail that down. Then I think one of the things we want to do is just understand the really complicated morphology of these radio sources. So it's not as simple as beautiful double lobes. There are lots of really complex things in there, types of sources that have never been seen before. So I'm just flipping through some DR2 sources that we selected in a project with a student, May Orton. She's working on writing that up at the moment. And we are going to be trying to use this morphological information to get better radio source models, and therefore do better environmental inference and better constraints on the feedback problem. So we're not there yet, but we will get there by understanding the detailed morphology. And another thing that will help us is the long baselines of LOFAR, because with the long baselines you can go down to sub-arc second resolution, and that allows you to measure the sizes of the small radio source population which are currently unresolved. That's really important if we're to understand those low power small sources in the LOFAR sample. So we expect to have we aim to have hundreds of square degrees imaged at those high resolutions in the next few years, and that's a capability that SKA doesn't actually have. So VLBI with LOFAR is going to be something that we will want to do a lot of while the SKA is still being developed. And some of you may have seen some press coverage about this recently. We just put a bunch of papers on the archive, I think this morning, describing some of the early work that's been done with the long baselines. So take a look at that as well. Okay, so I want to just summarize last slide. What we've I hope you will take away from this is that you can't really understand the feedback effects of radio galaxies without understanding their physics, and so that's what we're trying to do. That's the approach we're trying to take. And if you want to understand the effect of the population, you can't do that by looking at detailed observations of individual objects. It's a really great way of learning about the physics, but you can't learn about the population. So with LOFAR and the LOT surveys, and also with other instruments such as Meerkat, we're starting to get high quality, high volume samples of radio AGN. And that plus a detailed understanding of the source physics means that we can do inference directly from those surveys and work out crucial parameters like how much energy the AGN are putting into the local universe. Going forward, we hope to do this better with larger samples, better redshifts, and better imaging using the long baselines of LOFAR. And the goal is to understand not just on a not just for the whole universe, but on an environment by environment basis, whether the radio AGN feedback model really works. And of course, the techniques that we're developing for this will transfer forward into the SKA era, and I hope we'll be able to get some really good definitive answers from SKA, and the combination of that with optical surveys and X-ray surveys over the next 20 years or so. I guess I'm going to stop there, and I will stop sharing because I'd like to be able to see you guys, but I can share again if we need to ask questions about any individual slide. So I will pause and take questions.
All right, thank you, Prof. Martin, for the informative talk. Now we can now take questions. Okay, so there is one question here that's on the chat regarding the cavities that occur within the lobes. Is there any correlation between the number of cavities that appear and the age of the radio source?
Yes, so that's a good question. So the number of cavities that appear in something like the Perseus cluster, maybe I should just share that that picture again so that I can talk about it. Let's go back to that image. So if you look way back, here we are. Okay, so you look at this object, and you can see indeed there are many different cavities on different scales. And what we think is happening here is that this is telling us that the radio source has had multiple outbursts. So the inner set of cavities are a result of the current radio lobes, and then the next set of cavities out here are a previous outburst where the jet is turned on for a while and then turned off. There's evidence that another outburst is starting right now in the center. So what this is showing us is that the assumption that the jet power is constant in this particular object, at least, is not really valid. And if you look at the detailed X-ray observations of Perseus, the X-ray cluster is full of ripples that appear to have been generated by different AGN outbursts over time. So in that sense, you could say, well, the AGN is very long-lived. In fact, in these rich cluster environments like Perseus A, the AGN appears to be on all the time. So it lives forever. It just has episodes where it's active and episodes where it's quiescent. For the more powerful sources like Cygnus A, you can see over here, there's really only kind of one major cavity, and that's the size of that cavity is related to the size of the radio lobes. So we could assess the age of that source by seeing the cavity, but in fact it's easier to assess the age of that source by seeing the radio emission, which is the same size. But the nice thing about the cavity work in something like Perseus is that you can see the fossil record. Effectively, you can see imprints of past AGN activity that no longer produce any radio emission because it's disappeared. Yeah, it's a good question, and it does, you know, there is a connection between the history and the cavities. Yes.
Konstantinos, I can see your raised hand. You can unmute.
Yes. Thank you. Hi. Thank you very much, Martin, for a lovely talk and great results. My question is regarding, I mean, I would like your opinion regarding these filaments that are, I mean, lately seen in radio jets and bended radio lobes. Can you hear me? Sorry.
Yes. Yes.
Yes. Sorry. Yes. The ones that are mainly vertical, you know, seen that don't follow exactly the path of the jet. I remember, I think that Birkinshaw, exactly like this one on the right. Correct?
Yeah, that's right.
Birkinshaw, yes, and Worrell had mentioned this as something that might be some pre-existing magnetic flux tubes, or maybe I'm not saying it exactly as that, but I would like your opinion on that. I know it's something, of course, very new and unknown, but yes, your.
Yeah. So yeah, I mean, I think it's a really good question. So I mean, we've actually known about these for some time, and this so 3C4, this image of 3C40. I'm glad you allowed me to bring this up. We actually, this is the LOFAR image, but we actually had GMRT data that showed this same filament sticking out from the lobes in Sakali et al. 2008. So it's not new, and I have to say I don't understand it at all. So there is very often a double structure in these filaments, which I think is interesting, and you see that double structure in filaments that don't sort of have a logical connection to the plumes, such as in 3C40 here, but also in filaments that kind of do, such as the ones in NGC 326. But you see over here, for example, we have a filament that seems to be in completely the wrong place. You know, double filaments in these lobes in 3C83.1b that appear to be so. Because of that double nature, you could imagine this is some kind of flux tube, and that's the basis for Mark and Diana's ideas. Another possibility is that it's a remnant double trail because of a double jet of some object that's fallen in and just left a trail behind. So you can sort of imagine a galaxy might have fallen in here and left that behind, and then perhaps it's re-energized or compressed by the passage of the radio lobes. in NGC 326, we showed that there are a number of galaxies that lie along this extended region. And so again, it's possible that one of them came in this way and is now somewhere in here and has left this trail behind. But I honestly don't know. I think it's really interesting. And certainly some of the Meerkat results on individual objects are really striking. And I have others in LOFAR as well that I'm not showing here. So I think I can't explain this, but I think what is interesting is that the new data are really showing us features that we didn't expect based on the old observations, and the effect of really high image fidelity because of really good UV plane coverage is actually making a qualitative difference to our understanding of these things, which is really cool. And I hope at some point we will get some understanding and have some models that we can test against each other. For example, the polarization in those filaments, I think, would be very important to understand, and I'm sure Meerkat can answer those questions at some point.
Yeah, indeed. Thank you very much. Thank you. Yes.
All right, Bernard, I don't know if I can see your hand raised up. You can unmute and ask.
Thank you, Martin, for very interesting talk. This LOFAR data is really beautiful. I wanted to make sure I understood what you said earlier, that the very high mass galaxies almost always have an AGN switched on.
Yeah.
And a couple of questions on that. Firstly, is that true whether in clusters or in the field, isolated, or don't you get these very large galaxies alone in the field? And secondly, is there any indication as to, let me call it a spectrum, so that I don't mean optical spectrum. I mean, is there a sharp cutoff, or does this presence of AGNs gradually fade out as we get towards the smaller galaxies, or are you not able to say anything about that yet?
Yeah. So yes, I mean, good questions. I mean, we're using this rather crude measure of being turned on as just, does it have radio emission associated with it above a certain threshold? And that doesn't tell you anything about what that threshold is. Yeah. So to answer the first question, I mean, this is just all galaxies independent of environment, and of course, you don't tend to get objects that are 10 to the 11.5 solar masses in the void. So there is a correlation between the mass and the environment. But I mean, we're essentially it's everything. So whenever there is a massive galaxy, and it's usually going to be a massive elliptical galaxy, we know already it has a massive supermassive black hole. What this is saying is that the process that drives the jet activity is universal when you have those ingredients, and so it must presumably be something to do with accretion of, with secular processes in the galaxy and accretion of the hot phase of the galactic halo, which will always be there, onto the central supermassive black hole. So essentially, what I guess we're saying is that it's independent of everything else. It's just almost an intrinsic property of galaxies as you go to high powers. And I think that's what's striking about it. It's not that rules out at a stroke a whole host of models, such as triggered by mergers, because they don't happen at the right frequency. It's got to be something that's intrinsic to the galaxy. Now, what this emission is, and what do these sources look like? Those are questions that we can only really answer up at the bright end at the moment, because you go to this very faint end, the sources tend to be unresolved with LOFAR and indeed with everything else, and we don't really know what what the radioactivity is. We know it's nuclear, we know it's central, we know it's got a synchrotron-like spectrum, but we don't even really know whether these low power things are powered by jets or by something else like a wind. And there's some evidence that there are different mechanisms going on at the low power end. And lots of people are running around trying to make high resolution images of low power objects in this kind of regime, with rather inconclusive results. Some of them are little doubles, which you could classify in exactly the same way as we can classify the big things. And some of them are look unresolved, and some of them are kind of not really, just disappear at high resolution. And so I think the nature of those low power sources is still something we don't know about, and it's something I haven't really worked on because I like the big bright ones that you can resolve and understand the physics of. But it's definitely an interesting question.
Eric, may I ask a follow-up question?
All right, then, if there's no other question, we can call it a close.
Can I ask one more question, Eric?
Sure thing.
I'm happy with that.
Sorry, Martin.
Yeah.
You don't mind.
Yeah, go ahead. Yeah.
You've got very large samples now with redshifts and radio powers and so on. Are you able to tell us anything about the morphology of FR2s which go below what we used to call the power boundary between FR1 and FR2, and FR1s which go above that boundary? Is there anything that stands out about their morphology that would differentiate themselves from above and below that boundary?
Yeah, so there is some discussion of this in Beatrice's paper, actually, and the answer is yeah. So yes and no. For the FR2s, if there are low power FR2s, what they call FR2 lows in that paper, that are perhaps an order of magnitude below the expected cutoff, and they look exactly in every detail like powerful FR2s. You wouldn't know just by looking morphologically. They have the compact hotspots. They're not sort of masquerading. FR1s masquerading as FR2s. They really have all the features. And I think that kind of makes sense, because our understanding of where that cutoff comes from is about jet deceleration. And if you have an environment where the jets are not decelerated, close in the center of the galaxy, then you can generate those hotspots. FR1s above the cutoff, there aren't very many of those, actually. There aren't so many as the other way around, and they tend to be rather peculiar FR1s. So there you could imagine that that's a source that ought to be an FR2, but something terrible has happened to it. So there's some disruption of the jet where the normal FR2 like behavior has been temporarily interrupted, or else they're in really rich environments where so you get a certain fraction of the sort of so-called wide-angle tail objects are above the FR1, FR2 cutoff, but are clearly in some sense FR1s. But they often have relativistic jets and hotspots still, so they're just being really strongly affected by their environment, and thereby turned into they would be FR2s in a more favorable environment. So it's but the curious thing is these very low power genuine FR2s, and I don't think we fully understand why their jets don't disrupt close to the center and turn into FR1s. I mean, I should obviously emphasize that the trend is still there, and it's just that when you have samples of hundreds of thousands of objects, you start to see objects more objects that don't obey the trend. But I'm still very happy to say that, you know, most powerful objects are FR2s and most low power objects are FR1s. It really simplifies matters to be able to say that.
Thank you.
All right. Thank you everyone for attending. Now we can call it a close. Thank you, Martin, also for the talk.
Thanks everybody for listening.